Hi everyone, welcome back to Dave's Math Channel. This is my fifth video in a series on complex numbers, and today I'm going to talk about an important result called de Moivre's theorem. De Moivre was 18th century, early 18th century French mathematician. He came up with this important result regarding complex numbers given in polar form. So we're given an arbitrary number in polar form, a complex number, r times cosine theta plus I sine theta. Sometimes people write this as r cis theta. It's just a complex number with absolute value r and argument theta. So that's just a polar form of an arbitrary non-zero complex number. So if you have a complex number like that, and say you raise it to a integer power, positive integer power, n, what do you get? Well, de Moivre's theorem tells you what you get. If you take the number r times cis theta all to the nth power, what you end up with is you get r to the n times cis of n theta. Pretty remarkable. So basically, what that's saying is you're starting with an arbitrary complex number. You raise it to the nth power. The um, the absolute value of the number gets raised to the nth power, and the argument gets multiplied by n. So how do we prove this? There's actually a nice proof by induction, mathematical induction. And you have to use a little bit of trigonometry here. You have to use a trig identity. You have to use so you're starting with, I mean, first, whenever you're proving something by induction, you have to always start with a base case. So in this case, our base case is n equals 1. And for n equals 1, this is obvious because cosine theta plus I sine theta to the first power is obviously equal to cosine theta plus I sine theta. So there's nothing to do in that case, really. But you always have to start with a base case. And then if you want to prove this for all positive values of n, you use a trick called mathematical induction. You assume that it's true for some value of n. And we already know it's true for n equals 1. And then you have to prove that it also is true for n plus 1. So they do that here. I mean, you can write cosine theta plus I sine theta all to the power n plus 1. You can write that as cosine theta plus I sine theta times the number cosine theta plus I sine theta raised to the nth power. And then we're assuming, this is the induction hypothesis, we're assuming that this holds for n. So then we can write cosine theta plus I sine theta to the nth power is cosine n theta plus I sine n theta. I guess they're not using r in this case. It's not that hard to include r in the number, but they're not doing it here. They're just assuming that r is 1. But then they're using a trig identity. So you can then when you expand this product, you have a product of two binomials here. So you just expand it, you get cosine n theta times cosine theta minus sine theta plus I times sine n theta cosine theta plus cosine n theta sine theta. And then you can use what are called the addition formulas for cosine on sine. And I'm not going to go through those formulas, but you might have learned this when you learn trigonometry. You have these kind of complicated addition formulas for the cosine and the sine, and you just apply those formulas and see what you get. And when you do this, you find that you do, in fact, get the result you're looking for. You can prove just using those identities that cosine theta plus I sine theta all to the power n plus 1 is cosine of n plus 1 theta plus I sine n plus 1 theta. So that is the proof by induction of de Moivre's formula. Pretty nice. And this is a very nice result. I'm going to give you some examples now. So suppose we're given a specific complex number in polar form. I mean, actually, they give you here in rectangular form. Square root of 3 plus I. That's a particular complex number. And if we write this in polar form, we find that r is 2. R is just the square root of square root of 3 quantity squared. That's going to give you 3 plus the coefficient in front of I is 1. So you get 3 plus 1 is 4. Take the square root, you get 2. That gives you r. So z is just a complex number with absolute value 2. And then the angle, the argument, it's pretty easy to compute too. It's just the arctangent of 1 over the square root of 3, which you probably learned is equal to 30 degrees or pi over 6 radians. So you can write this whole complex number is 2 times cosine pi over 6 plus I sine pi over 6. And now we're going to raise this whole thing to the 6th power using the Moivre's formula. So the first thing we do is we raise the argument, which is 2. I mean the absolute value, which is 2 to the 6th power. So your new absolute value is going to be 2 to the 6th. There's 64. Your new argument is going to be 6 times pi over 6, which is this pi radians. And cosine of pi, that's cosine of 180 degrees, that's -1. And the sine of pi, or the sine of 180 degrees, is 0. So the polar form of the result is -1 plus 0I. You can leave the 0 out. So you just have 64 times -1, which is -64. That's your result. Pretty nice. So, let me just show you another little bit more complicated example. This is basically the same example, except here we're raising to the 7th power. So instead of multiplying, and here they do it in degrees. So instead of multiplying the argument by 6, they're multiplying by 7. That's going to give you cis of 210 degrees, which if you work that out is negative square root of 3 over 2 minus 1/2 I. That's going to be your new um, sort of unit complex number, but then you have to multiply that by the modulus and the absolute value, and the absolute value of the number you started with was 2, so we're raising that to the 7th power. We get 128. So when you simplify everything, here's what you get: minus 64 square root of 3 minus 64I. So you can pretty much apply this to any complex number you want. This was a pretty complicated example. But another thing that's really nice about de Moivre's formula is it can go backwards. You can compute nth roots. If you just invert this formula, since it's true when you raise a number to the nth power, it's also true just by inversion that it works for nth roots as well. So if you're given a number z equals r cis theta, I'm not going to say cosine theta plus I sine theta, I'll just say cis, it's easier. So you start with r cis theta, you want to take the nth root of that. Well, you know that the absolute value is going to be the nth root of your originally absolute value. So in this case, the nth root of r, that's just the length of your new vector. And now you're going to get cis of, you might think it's just cis of theta over n, but actually you have to be a little bit careful here, because it turns out that there's actually there's not just one nth root, there's n nth roots. You can add, you could have added any multiple of 2 pi or 360 degrees to theta when you started, because 360 degrees is a full rotation. If you increase the argument by any multiple of 360 degrees or 2 pi radians, you get back your original complex number. So when you're taking an nth root, remember that you have to divide the argument by n. So you're also dividing the multiple of 360 degrees or of 2 pi radians by n. This gives you this extra factor of 2 pi k over n. You have to let k range from 0 to n minus 1. This is going to give you all the roots. So in general, that you're going to get n nth roots, and they all have the form nth root of r times cis of theta over n plus 2 pi k over n, where k ranges from 0 to n minus 1. So that's the general formula for finding all the nth roots of an arbitrary complex number, non-zero complex number. And here's a little bit simpler form of that same formula. So here they write alpha instead of theta for the argument. So, well, actually, I guess the original argument would have been n alpha, and you're taking the nth root. I guess the original argument was theta, so alpha is going to be sort of theta over n, but in general, it's theta plus 2 pi k pi over n. This is just the general form of the arguments in each of the roots of the nth roots of your original complex number. So that's a nice formula to remember too. And I think I should show you some examples now. So here's an example where we're finding the cube root of a given complex number. And this is just the cube roots of 1. And when you were learning real analysis, you probably learned that every square root, there's 2 square roots of every real number, or every positive real number, just positive and negative square root, right? But then you probably learned that for cube roots, there's only 1. In general, for nth roots where n is odd, there's only 1 real root. And that's true if you're only worried about real roots. But if you're worried about complex roots, it turns out there's actually nth roots for all n. And you might have only learned that when n is even, you only get two roots. So for instance, there'd be two real fourth roots. In general, there's two real nth roots if n is even, and there's one real nth root if n is odd. But if you're working with the complex numbers, there's always n real nth roots of any given complex number. And here are the three cube roots of 1 written out. So the first one's obvious. That's just 1. That's when you know your argument of 1 is 0 because it's a positive real number. And then when you're doing the cube roots, you remember you get this 2 pi k over 3. K is either 0, 1, or 2. So this is going to give you 2 pi over 3. It's going to be 0, 2 pi over 3, which is 120 degrees, 4 pi over 3, which is 240 degrees. So the cosine of 120 degrees, or 2 pi over 3 radians, or cis of 120 2 pi over 3 radians is going to be minus a half plus the square root of 3 over 2 times I. That's your second cube root. That's an imaginary number. And then you get its complex conjugate. You get cis of 4 pi over 3, which is minus 1 half minus square root of 3 over 2 times I. So you get 3 cube roots of unity. And I think a picture, they say a picture is worth 1,000 words. So here's a picture of the 3 cube roots of unity. And notice that they form the vertices of an equilateral triangle. That's a nice feature of nth roots. In general, the nth roots of any non-zero complex number always form the vertices of a regular n-gon. In this case, a regular triangle or an equilateral triangle, if you like. So these are the three people usually call these the cube roots of unity, really the cube roots of 1. I guess they like to call 1 unity. So these are the 3 cube roots of 1, or the 3 cube roots of unity. Pretty nice. And you could do this for arbitrary n. So this is n going from 1 to 9. So these are the nth roots of unity for n going from 1 to 9. And for 1, it's no surprise. There's only one first root of unity. That's just 1, and that's the point on the right. And so forget about the picture on top. These are the fifth roots of unity. But if you're looking at the 9 pictures on the bottom, the first picture top left is the one first root of unity, just 1, which you can think of as a vector of unit length going to the right. And then for the square roots of unity, you have both 1 and minus 1. So now you got 2 points, one the negative, the other. This isn't n-gon yet because we only have 2 points. But now when n is at least 3, we get the vertices of an n-gon. And it's the same kind of pattern. I mean, you get these angles that are, the first case you go around 360 degrees or 2 pi radians. Second case you go around 180 degrees. You just keep dividing 360 degrees by n. In the third case, cubes of unity, they're all separated by 120 degrees. For fourth roots of unity, they're all separated by 90 degrees. Notice the fourth roots of unity, I think, are pretty interesting. You get 1, I, -1, and -I. I is what's called a primitive fourth root of unity. Remember how I said, I think in the first video I made, I said I to the fourth power is equal to 1. So that means that I is what's called a primitive fourth root of unity. Primitive just means that there's no smaller root power of the root that's equal to 1. 4 is the smallest power, a positive power of I that's equal to 1. So that's what's known as a primitive nth root of unity. It's just a complex number such that the smallest power of that number gives you smallest positive power of that number gives you 1. So the fifth picture is the fifth roots of unity. These are all primitive. It turns out that if n is prime, every unit of unity is primitive. Sixth roots of unity, you got 2 primitive roots. We've got the one with an argument of 60 degrees. And you've also got the one with an argument of 300 degrees. Those are just the ones on the top right and the bottom right in this pie shape thing. And then you've got the primitive cube roots of unity. Notice that the cube roots of unity are also 6 roots of unity. And then you also got -1. So these are your 6 roots of unity. And you can do this for any value of n you want. So you get all n roots of unity this way, which I think is really nice. And I guess that's my video. That's my video on the Moivre's formula for calculating arbitrary positive powers or positive roots of arbitrary complex numbers. That concludes my video. Thank you for watching. Long live math, and we'll see you next time.